Okay.
Welcome everyone to the CS Education Zoo. We're on our second episode. We're very excited to be back. I'm here with my co-host Will Bird, and he's going to introduce our special guest for today. So, Will?
Hello, welcome to the second episode. Today's guest is Rob Simmons, who's a friend of mine from Carnegie Mellon University, and he's been involved for the last couple of years in teaching some really exciting new courses and revamping the intro course at Carnegie Mellon, which, as you might know, is one of the best computer science schools in the world. And they're doing some really cool stuff, especially with teaching imperative programming, which is kind of interesting because CMU, from a programming languages standpoint, is known as a hotbed of functional programming languages. So it's curious to find out how they teach imperative programming without having to hold their nose, because a functional programmers, once you start talking about imperative stuff and side effects, they start getting antsy. So without further ado, here's my friend Rob.
Hello, and thank you. I'm excited and humbled and nervous, and to be on this program. I guess you suggest I start with a little bit of background about myself. I was a undergraduate at Princeton University, and in my sophomore year, Andrew Appel, who's faculty at Princeton University, sent an email to the CS undergrad saying, if you're a student that started out taking some advanced math courses but decided, no, I think I'll go with computer science, you should take this course on automated theorem proving. And that course led to a research project, which led to another research project with David Walker, and that was what set me along the path to end up at grad school at Carnegie Mellon. And then at grad school at Carnegie Mellon, I worked a lot on the logical frameworks for specifying both functional programming languages but also imperative programming languages, which was one of the ways that I ended up in the course that I'm teaching now. And once I was done with my PhD, they offered a postdoc, which they've done for a number of Carnegie Mellon graduate students, to get a little bit more experience in teaching in a postdoc situation before we head out into the world. And for me, I got a little bit more experience teaching and then decided not to head out into the world, and they decided they would like having me around, and I enjoy Pittsburgh very much, and so decided to stay. So that's where I got to where I am now.
Can you talk a little more about the postdoc and the teaching? Because that seems unusual to me, because I've done a couple postdocs now, and most of those postdocs that I know of seem to be more research oriented. Mm-hmm. So can you talk about that and kind of how that came about and how that worked out? Does that seem like a good idea that other schools should do?
So it's an interesting. It's an interesting postdoc. It's not like you say, it's not the usual model. In the years since I did it, they have somewhat tried to formalize the process as the Mark Stellick teaching postdoc. I think an interesting, maybe not that unusual aspect of Carnegie Mellon's PhD curriculum is that for our PhDs, you have to TA twice as a graduate student in order to get a PhD in the computer science department. That's part of our education, but you may just TA twice. I, as a grad student, really focused on the research aspects of my PhD and didn't, had a great experience teaching, TAing two courses early on in my grad school career, but as I was preparing to leave the PhD program, and I was thinking about, this idea of going and potentially looking for, doing some more research, perhaps in a postdoc, but then looking for possibly tenure track positions, which wasn't ultimately the route I decided to go. But the idea of possibly looking at a tenure track position and being in a position of, all right, now it's time to start your research career and get your NSF career grant and start advising grad students. And by the way, here's 100 undergrads, and you've TA'd twice, struck me as really, really frightening. So I was very appreciative that, as I was evaluating what my career path was, they had the option of staying on, and they do it strategically. They needed some help with one of the courses that they were teaching, and I was in a position, the course that I'm now teaching, Principles of Imperative Computation, but I was able to teach that course. It's a large lecture course. We had, I think, 275 students between 2 lectures when I first did it, and now it's even larger. And I was able to work under the mentorship of both my PhD advisor, Frank Fenning, and Tom Cortina, who has been in CS education for decades, and was able to work with both of them for the first semester, as really, I finished my PhD, and as I was working into moving into this new role, I found that mentorship opportunity absolutely amazing, and really, really helpful. It was a big part. The fact that I was able to do a real teaching of a large intro class as a postdoc. I certainly wouldn't have ended up where I am now if I hadn't been able to grow into that role in that way. So,
very cool. Steve? Yeah, that's awesome. Yeah, that's exactly what we want to hear about. Okay, Steve, do you have a question?
Yeah, so you obviously you mentioned the imperative computation course, and a lot of universities have their CS1 course, their intro course, in an imperative language. We've switched away from that recently, and I'm kind of curious what you see as the key ideas that students need to struggle with when they look at imperative computing from the outside.
So it's interesting. So we talk about. The course is named Principles of Imperative Computation. Really, it's in most other universities would be most closely identified with the Data Structures and Algorithms course. The course that's much like the one that Kim Vol was talking a lot about teaching last week. So it was, we're emphasizing data structures. We're emphasizing, however, the aspects of data structures in the Principles of Imperative Computation class that are primarily data structures that act via mutation. So if you think about that, in-place sort is one of these. Hash tables are really there are ways of doing functional hash tables, but they usually involve something like, but frequently one of the ways that you implement functional hash tables is with benign effects. And so we really do work on what are the data structures that are core to dealing with operating by mutation. In fact, one of the things that we teach in the course is graphs, and I kind of decided the most recent iteration of the course that really the only reason we teach graphs is to explain union find. Because graphs, like we need to talk about, graphs, we're teaching that because future courses are going to expect them to have seen, adjacency matrix and adjacency list representation of graphs. But it also is fantastic when we can get across this really cool idea of imperative computation, which is the union find data structure. I think it's. But you asked the question, what are the things that people struggle with? I think that the notion that I found students struggling with the most, and especially we have one assignment that's always incredibly conceptually difficult for students because it involves both recursion and mutation. And so you have a function that's going to change the state of a data structure, and when it returns, it has to put it back in the same state. And that is really interesting to watch students slowly piece through what that means, because it requires them to think about the recursive call as I feel like it's in a different, there's something extra about what's going on with the recursive call than students usually have to think about when they're working with functional programs. The other reason that that this notion of thinking about how do I restore the things that I've broken leads to a lot of the key ideas that that we look at over and over in the course. The idea of having invariants that are violated partially and then restored. And I think the core example of that is you've got a heap data structure, a priority queue implemented as a heap, and for a while you have this data structure that is completely not a heap, but that because it's only violated in one place, you can keep fixing it, and eventually you'll get back to where you started. I think that those are things that we can very, very nicely capture in the way that our course does reasoning about imperative programming, and that's maybe the next thing I should speak a little bit about. But there are other things about, well, you've got a function, it's going to change the world, but it's got to put it back in the same place as when you started. Those are things that I've seen students really struggle with in an interesting way.
But that's interesting. So, so let me see if I can summarize here. You talked about the idea of a data structures course is a good way to bring in imperative programming because data structures are a natural place where we gain a lot of traction from mutation.
Some data structures, right?
Yeah. And then also this idea that maybe a key way to think about mutation is to think in terms of invariance and the idea of breaking and fixing an invariant iteratively, because that sort of gives you a baseline of a functional feel, and mutation becomes small local deviations from that functional feel instead of jumping off into the deep end of reasoning about mutation.
Absolutely, and I think that the course is really designed, and so the unique thing about the course is that that it's a data structures course, but it focuses on imperative data structures in particular. One of the reasons that we focus on imperative data structures in particular is there is a different course, and this is sort of the larger context of our curriculum, that deals in parallel and functional data structures and handles those as a single entity. And so, there are these two threads of introductory computer science that work in tandem in Carnegie Mellon. I think one of the ways of saying it is that we in our course, we really focus on quicksort because in-place sort is cool. And we mentioned merge sort, but we really focus on quicksort. And then there's the functional programming class that really emphasizes merge sort because merge sort's cool, and mentions quicksort. And these are these happen at the same place in the curriculum. So a lot of other schools have the course where you start moving from thinking about programming to thinking about computer science, and we very much have two. And there's a functional programming course, but the imperative programming course is one that is the one that I've been more involved in. And absolutely, the entire goal of the course is to allow people to think about code in terms of contracts and invariants. And we have a language that is a C-like language that we've constructed for this course. It's called C-Not, but the core idea of this language, other than the fact that it doesn't have undefined behaviors, and it's quite a bit smaller than C, and it has array bounds checking. But really, the thing that we have are that makes it important for teaching the course is you can annotate functions with checked preconditions and checked postconditions and checked loop invariants that are, you can annotate a loop with a loop invariant. It looks like a special form of a C comment. It's got the, I'm just going to draw this above my head. So we've got preconditions that are written as these comments that start with an @ of requires, but we also have postconditions that can be written into the program and optionally checked at runtime, and then this for the way that we teach the course, absolutely a key idea for what it means to make imperative programming a tractable problem, that you've got to both describe what the data structure invariants of your full-scale data structure are, so that whenever you enter or leave the library interface of something like a hash table, you know that all of the everything in the hash table is, if you do separate chaining, it's a bunch of buckets. Every bucket contains a bunch of distinct keys. The keys all have a hash value that says that they are where they're supposed to be, and it's these invariants of the data structure that allow us to reason about that allow us to work with our code at scale. And so that's sort of talking about the preconditions and the postconditions of saying that you're keeping your data structure invariants right. But then on a smaller scale, when you're in the middle of an algorithm, or you're in the middle of a loop, you're searching through your array, you're sorting an array, or you're fixing up your heap in a heap insertion or heap deletion, then having checked loop invariants is a really powerful way of saying, all right, what does it mean to have code that is consistently staying correct over time? The really cool thing about this from a mathematical perspective is that a loop invariant, a loop invariant is just an induction hypothesis of the proof that the program is correct from a certain perspective. But because we're able to say, oh, these are statements that are in your code, they're checked at runtime, we never actually talk about induction. They're actually, we don't have as a prerequisite the course that teaches induction for computer science. So we're assuming very little other than the fact that students can write contracts, understand what it means for a contract to fail at runtime, and with that, that becomes the basis of how we make imperative programming sort of a reasonable exercise.
So this sort of feels like Eiffel meets C.
I think that, yeah, we are looking for, I can't unfortunately say, like, I don't have a thorough enough understanding of Eiffel for that, but there are a lot of work in these sorts of more specification-oriented languages. And when Frank Fenning, Rob Arnold, and William Lovis looked into the design of CNOT, they were looking at some of this other language, these other language designs, and the work on contracts that's going on in a lot of different places. Yeah.
Very interesting. So Kim Boll said last time that she thought that teaching people how to do proofs seemed especially hard. Mm-hmm. And can you comment on that and your experiences, or the sort of CMU experiences with that? So
Kim talked about, yeah, I actually have been thinking a lot about what was effectively Kim Boll's point, which is that you can allow people to, you're teaching people to do proofs, and to evaluate proofs and to read through proofs, but what you're really trying to do, I think I'm paraphrasing her correctly, was to have people able to um, have a program on their own that doesn't have a proof yet and work through that proof itself. And that's really difficult to automate. That's really difficult to teach students an algorithm for. And I think one of the things that I've been moving towards, and this is probably going to be a big give and take over the span of years, is that because we're teaching this course, in many cases, if CS freshmen come in with programming experience, then I'm teaching them the first semester of college. And so one of the decisions that we've kind of been moving towards iteratively is that we don't actually ask them to come up with new proofs on their own. And that is to say that we don't ask them to synthesize loop invariants unless it's a program that is very much like the one that they've seen before. So if there's a loop invariant that says, oh, the thing inside the loop is always positive and less than the upper bound, then we teach that in class over and over, and so that's the sort of thing that we might ask them about on an exam. Maybe we'll go decrement the loop instead of incrementing the loop. Oh wait, that showed up the wrong way on video. They'll decrement instead of increment. There we go. And so we've got these. What I found is really important is the way that the students know that a proof is wrong is much more important at the level that we're teaching them than them actually being able to come up with the new loop invariant on their own. And so this is actually, it's a little bit lower in the hierarchy of understanding to say, here's a loop invariant of a loop. Either give me either explain why this loop invariant is preserved by every iteration of the loop, which is just a matter of we're teaching them to symbolically execute the loop body forward for one iteration and say if the loop invariant was true before, then how do we say that the loop invariant is true afterwards? So we teach this notion of symbolically evaluating a loop to say that the loop invariant is always preserved, or we say, give an example of values that the assignable variables could be set to at the beginning of the loop, such that the loop invariant holds initially, the loop guard holds initially, and the next time we get to the loop invariant, it will evaluate to false. And there we're not asking a question that they identify as being deep proof of correctness. We're asking them, like, here's some code, break it. And that's the thing that's still very difficult for them to get. But I think that when talking about where I can expect most of the students to get to, being able to explain to them why a proof doesn't work in terms of a counterexample that you could run, and that the program would fail because you would violate at runtime a loop invariant, and it would throw up the loop invariant on this line evaluated to false. That's an incredibly useful artifact of being able to execute these contracts at runtime, is what we're doing when we're teaching them to reason about code, is we're teaching them to evaluate and create proofs. But we're asking them to create proofs usually once they already have a loop invariant. And then you're almost there, because once they learn to be, what's the word I'm looking for? Not confrontational, adversarial. Once they learn to be adversarial about their own statements of correctness, once they learn to say, oh, I think this is the reason that my code is correct, but if I'm wrong, why? Then now they're in the process of saying, okay, I've got a loop invariant that's wrong. I'm going to have to change it. Okay, now I have a loop invariant. Is it right or is it wrong? Can I move on from here, or am I going to have to change that? So that sets them off on the cycle of being able to iterate. in future courses with their proofs, but it makes it a much smaller question of, all right, I've got a proof, am I going to be able to come up with a or I've got a set of contracts. Am I going to be able to come up with a proof that these are correct, or am I going to be able to come up with a counterexample that shows that I have a problem? So, and at that point, we're having them reason about proofs, but we're also having a conversation about testing, which is another big deal for students at this level.
So you have these two courses that are at the same place in the curriculum, one with the imperative programming and the other one with the functional and parallel data structures. Is that?
Yeah, that's correct.
And can students take those in both orders, or do they have to take one before the other?
So let me draw a thing. So we've got, the way our curriculum works is we've got just a programming course that we get students that are coming in, starting from zero. And then we have two courses that do descend off of that in either order. We've got my course, or the course that I've been primarily involved in, which is working with imperative programming. And then we've got another course that is working with functional programming. And yes, students can take the imperative programming and the functional programming course in either order. The reality is that they take them either imperative and then functional, or they take them at the same time. And the reason for that is that the functional programming course expects that they have finished the mathematics course called Concepts of Math, which is like induction, how do we reason about discrete math types of things. And so because we have that as a co-requisite, they can take it at the same time, and the other course has it as a prerequisite. People have either gotten to where they take them imperative and then functional, or they've taken them at the same time. It is meaningful, though, that they can take them at the same time, and a number of students do that every semester. And then I was mentioning also there's the parallel data structures and algorithms course that that then has both my course, the 122 imperative programming, and the functional programming course as a prerequisite. And so you kind of go, you start up here with like basic programming, and then you go down to working with imperative and functional programming as two ways of looking at the fundamentals of how we program as computer scientists, rather than how we program in order to, programming as a mathematical discipline rather than programming as a as an activity. I actually don't know what the way I want to say the difference between the view of programming that happens here and the view of programming that happens up here. But then there are all these courses where we've got parallel data structures and algorithms. There's also a course that deals with object-oriented programming and programming in the very large, and that's a Java-based course. And that's another course that has both the imperative and the functional programming courses as prerequisites. And then there's also like a bunch of math courses that live over here, so that if you don't want to ever deal with imperative programming at all, you don't really have to. Not many people do that, but then there are a lot of people that are interested in hardware, or they're electrical engineers, and the systems programming track is all sort of over on this side, where it relies on the imperative programming course without expecting that people have done functional programming.
Well, thank you for that overview. It's interesting to see how it's structured. One thing that I think a lot of people have noticed teaching functional programming is that often the students who haven't programmed before seem to do better than the students who've been exposed to imperative programming. Mm-hmm. And I'm just curious about your experience with that. Obviously, you have a much more sort of rigorous approach to teaching imperative programming than most cases. Mm-hmm. But do you see a difference between the folks who have who are taking the courses at the same time versus the people who take imperative first and that sort of thing? Is there any?
Yeah, it's an interesting question. So the course that the introductory to the intro programming course is taught in Python, and I think that Python has the quality of um, while being and uh, the students that are coming in that haven't programmed in C into the imperative programming course are um, um, are I think a little bit more. There are definite things that we have to teach them. So the idea of pointer structures and the idea of indirect reference and having an array that's no longer a dictionary, it's now just a contiguous piece of memory, which is where which is roughly the way we're looking at things. Having and pointers in particular, that's not something that the students that have just done Python have as much experience with. Whereas I think that students that have done C programming already, or they've been doing C++ programming, or they've even, in certain cases, if they've been doing Java programming, they have a little bit of a heads up there. And my experience is that the functional programming course is not doesn't have quite as much differentiation based on experience, and in fact has more differentiation based off of mathematical sophistication coming in. And I think that that's representative of the ways that the two courses are taught. I mean, I think that when people are discussing starting students on functional rather than imperative programming languages, if you're talking about just starting, then you're up here, not down here. And so I think that this course could be taught in a lot of languages besides Python, and it's mostly contingent that it's taught currently in Python. But that's it's up here that the distinction I think you're talking about is really relevant.
So I wonder if I can steal the conversation and go in a different direction, Will. Does that sound okay?
Go for it.
All right. So Rob, I will ask a selfish question.
Okay.
I get a lot of students coming into my office, and they're anxious about the exam that they just took. Maybe they're anxious because they got the grade back, or maybe they're anxious because they're just terrified that they'll get the grade back. And they ask me what to do for the next exam. And honestly, I think, like a lot of us, I had a lot of us who are teaching CS. I had a relatively easy time compared to my students in my CS courses. So I do my best to give them some reasonable advice, but I find this a really challenging situation. I was hoping you could talk about what you do with students in that situation.
Okay. So I've this is something that when we were having a discussion about this beforehand, I said that I'd been thinking about a lot lately, but I've been thinking a lot about it lately because it's because it's such a tough question, and I don't feel very. I think it's potentially symptomatic of a larger problem that I don't know much of what the answer to that is, and that we can get a number of us in the room and we really don't know how to actually approach this problem. I think that because the simple way in which we try to go about these, and I don't know if the places where you've been operate roughly the same way, but there are practice exams and there are solutions or exams from previous semesters, and those are posted online, and students can do those, and students can do them, and can check the solutions and compare those to their own answers, and that is in many ways I think where we stop. That's the best answer that a lot of us are able to give, and that's a well, I feel like there needs to be a better answer to that. It's a question that that has gnawed on me a little bit lately, as I taught this very fast 6-week course that's usually a 15-week course. So rather than 2 lectures a week, it was 5 lectures a week. And so there was there were students that were asking me this question. In that case, everything's moving at kind of blinding pace, and so if you wonder, how can I encourage people to catch up? They really just need time to. That really might just need time to catch up a little bit. I think one of the things that has, one of the things that we want to do ultimately with our curriculum is start using some online posted tutorial style videos as not as the primary mode of delivery of the course, but as another way that we're presenting the course as another mode for people to gain some of the content. And it may be that one of the ways of approaching this is to have more focused questions that are dealing with particular aspects of so that students don't feel like they have an enormous attack surface to hit on. But honestly, I'm lost. If other people want to have thoughts that are in the Hangout, I'd love to hear from them as well, or from y'all.
I feel like I'm in very much the same situation as you, in the sense that I think this is important, and I have some things that I do, but I'm not totally confident about it. I'm going to paste in a URL for tomorrow's professor posting that I was looking at recently, which might it kind of crystallize my thoughts, and maybe we can post this on the website after the chat.
Sure.
And that talks about these things called exam wrappers, which are basically just little thought questions that they propose giving to students after the exam, and part of those thought questions are, how could you have prepared better? And they say, well, maybe you can take these responses that students give, and you can hand them out to them 2 weeks before the next exam, and you can say, last time you said maybe you should do this before the exam. Well, now here we are, it's 2 weeks before the exam, maybe you should do this.
Maybe you should do this. One of the other things that I have, a very specific situation, is that there have been a small number of students that have been performing quite well in the course, but have just been wrecking the exams, and they were doing the work, they were trying. And a lot of cases, that's a very, one of the specific ways of dealing with those students is I've offered to proctor the exam for them, in that I would be in my office for an hour and a half, and they would sit down and they would take an exam. And I think that one of the reasons that that's useful is that sometimes students have that are working through the exam on their own have it's kind of like how your blood pressure goes up when you're in the doctor's office, and maybe normally you're fine with your blood pressure. That sometimes actually being in the setting helps them realize what's hurting them for the exam, but they're not focused on the fact, oh, I'm failing this exam right now, I'm failing this exam right now, I'm failing this exam right now, this exam that matters. It's that, oh, okay, I realize that this feels really different than when I was not taking the exam, when I was taking the exam in my own room. So that's part of what needs to, that's part of the deal. And in certain cases, that's a real profound anxiety issue that we need to work with accommodating with the students, that they're perfectly able to do the exams, but they have anxiety that's preventing them from doing well, and so then there are steps that can be taken through our on our own or through the disabilities office at Carnegie Mellon that have helped a lot of people and have really turned students that were heading for C's in the class to students that were clearly getting A's in a class. So that also seemed worth mentioning.
So, Will, are we ready to start throwing open for Q&A? I see we've got a question in the chat window from one of our audience.
Yeah, why don't we see what sort of questions people have? And so one question we have, I think the name is Anas. Hopefully I'm pronouncing it correctly. And the question is, Rob, I'm curious how student feedback may have affected your teaching style. Is there anything you stopped doing or continued doing based on student evaluation? If so, what impact did that have on student learning?
Mm-hmm. So I think that one of the, and this may be somewhat apparent from listening to me talk on a video, I jump around a good bit in conversation. And I've definitely gotten feedback about jumping around a bit in lecture. And I found that a way in which I've tried to approach that is, again, instead of having a one-level outline of a lecture, I need to have like a 5-level outline of a lecture so that I know what the conceptual dependency is. I can't say I always do this, but the lectures that I give and that I'm really happy with, I frequently do have a very detailed outline of not just where of the order in which concepts need to be presented in, and of the different ways in which, based off of what student responses are, that might get rearranged. And so frequently you'll get a great question and that means that you have to skip forward, or you'll get a great question and that means that you realize that you missed something a couple of steps back. But the classes that I've taught, we don't use slides as a primary mechanism at all. We're working on the Blackboard and we're working in a coding session. It's kind of a more improvisational style, and I think that's important for the way that we teach the class, of making sure that students stay engaged with what we're talking about. But the best good improv still has pretty structured plot lines ahead of time. It's the dialogue that is done, sort of live, and so I think that that there have been certain cases where, for the lectures, particularly lectures that involve drawing trees. Drawing trees is in like a tree rotation. If you try to draw that with like an eraser, then the blackboard just ends up uniformly white. And so there have been some lectures where I've moved from having the chalkboard for all of the lecture to having the chalkboard for this part of the lecture, but then rather than animating this diagram on a chalkboard, I animate that with an online demonstration or with a set of slides or something like that, because otherwise I'm spending all my time erasing and making sure that things are thoroughly enough erased, and I jump around enough in conversation already that it's very helpful for me to have a little bit more structure. And it may be that as I continue to learn and grow, I'll be able to move back to that style that, like I said, my mentors I originally saw using, but I do try to remember that the people that I originally saw teaching this class had been respectively doing what they're doing for multiple decades, and I've been doing this for multiple semesters. That's very different. So I think that's one example of just how student feedback has affected my teaching style. I think that student feedback has also been very important as we take exercises and we turn those into what are the exercises that are the most helpful for helping students learn the learning objectives of the course that we're teaching. And so I think that the place where student feedback has had a really profound effect is if everyone is saying, oh, this assignment is particularly hard, or everyone is saying this assignment is particularly easy, that doesn't necessarily tell me that I need to make this, that that doesn't necessarily directly give me what has to happen to the assignment, but that's really critical feedback in understanding where what the role of those assignments inside the course is. And maybe an assignment that's particularly easy, there can be a twist that causes someone to look at it in a different way that they might not otherwise have. And so I think that in terms of my overall teaching, I've found student feedback to be particularly critical in not just front of classroom assessment, but in terms of the larger picture of assessment and in what the assignments are and what even what the exam questions are.
Thanks. Anyone else? Okay, Chris, did you have a question? Oh, sorry, that's an S. Okay. Yeah, thank you. Let's see. Are there any follow-up questions or?
Yeah. I guess for Anas, I would be curious if you were asking particularly about lecture style or about sort of the larger picture of what it means to be. Oh.
Yeah, my question was general for sure, but I think I was probably focusing on lecture style.
Mm-hmm.
I have a follow-up if no one else has a question. How do you handle feedback that you're not sure about? That's common, but students just say it because it's inconvenient. How do you deal with feedback that you think is not really going to improve your teaching or improve student learning? How do you convince students that, or do you experiment a little bit if you're not sure? Like, how do you handle that?
Mm-hmm. So I think that it's important for feedback that, I mean, it's been really difficult for me to get used to dealing with negative feedback. But if you have a course with 300 students, there's going to be negative feedback, and that took a good bit of growth as I started this, and I knew that it wasn't like this was surprising. Like, the first time I got teacher feedback, I was like, it was mostly positive, and there were a couple of negative comments that I thought were really true, and those hurt, and there were a couple of negative comments that I thought weren't true, and those really hurt. But the question is, I think that, and then this maybe gets to the heart of your question, I've gotten better at understanding and integrating the feedback that I think is correct. You jump around and lecture a lot. Yes, and that's a thing that I need to be able to improve on, and it's also, but it's also kind of a weakness of mine, and I need to, and it's not something that I'm going to change overnight. And so those are things that are useful for me, understanding sort of an honest assessment of myself. Then there are and actually I find that one of the advice that I think is wrong about how to teach the course most frequently comes from my TAs, because I'm teaching like I said, I think we're going to have 375 students in my course in the fall, 2 lectures, and so I'm going to have over 20 TAs that are going to be helping me teach this course. And they have opinions. They have opinions. And a lot of them are absolutely fantastic opinions. But sometimes I really do disagree with those, with what they think about how a various part of the course can be run. I'm trying to think of a particular example. Maybe one will come to me, but I'm not thinking of it right now. That's usually easier feedback because I have the ability to have a discussion about it. And I think that if there's feedback that I disagree with that I can't form an argument for, then there's probably a problem. Even if I think it's wrong, I need to or even if I think it's not helpful or not particularly useful, I need to be able to know. I need to know how to address that concern, because if a TA is bringing it to me, it's also probably occurred to 25 students that haven't mentioned it to me. But I mean, the critical part, I think, is really forming models of what the course is supposed to be doing, and being able to say that is a complaint that, to a certain degree, may even indicate that the course is running as expected, that all is going according to plan. I'm getting the complaints about the pointer assignment being too hard. All right, that's good. They've figured out that pointers are difficult, and that wasn't going to, that there are certain learning objectives that really do require people to struggle up against something and then recover. And so I think that, especially in terms of TA feedback, it's it's important to have reasons, but it's also really okay for people to want to teach a course differently. I mean, one of the nice things, and it's really the gift about being in this set of students, is there are also a lot of really valid ways to get these students through the learning objectives that we want to teach them. And to a certain degree, all I'm trying to do is make sure that, or the most important thing for me to do is make sure that I don't actively get in people's way and actively discourage people that would otherwise be great at this. And so that's also, there are multiple categories of that sort of feedback that I don't understand, and feedback that I don't understand that's saying this just burnt me out and I don't think there was any point to it, is stuff that even if I disagree with, I think I have to take more seriously than I would teach this differently in this way, I would do this part of the course differently in this way, because there are a lot of ways in which this could be done really successfully. It's not the sort of thing that we even want to find the single best way of teaching. That's not necessarily a coherent idea.
Very good, thanks. Mm-hmm. Well, I think Chris actually has a question.
Yeah, am I unmuted now?
Yep.
Mm-hmm.
Yeah, so I'm wondering what are some of the unique challenges of teaching first years as opposed to older college students?
Mm-hmm. So, like I said, the students that show up at Carnegie Mellon, they may be in my course the very first semester, and that means that they do not necessarily have a lot of skills that you can expect students later on to have. There's going to be a lot of people that, I mean, there are going to be an awful lot of emotional and personal and every kind of difficulty. They're working out a lot of stuff at once. I think that the primary thing that in the design of the course and the way I've changed it, we've really taken account of the fact that we're teaching first years is we've had to decrease the size of every assignment substantially. So when I first started teaching this course, we had about 8 assignments that included both a written theory component and a programming component. And now that I've been teaching this, I think that I can say this with a clear conscience without actually adding more total work. We now have about 11 written assignments and I think 12 programming deadlines. The way that we changed the programming deadlines is we basically split up 3 of the assignments in order to have weekly assignments that were all smaller chunks. So rather than having one assignment that you had 2 weeks to work on, so that you could delay until the last day and have far too much to do, we required them to do a little bit of, we did a little bit of that time management for them, because I think that it's the most obvious way in which most of the students we're going to deal with, because they're first years, is absolutely just straight up time management. Because we're dealing with first years, there also are going to be a lot of cases, a couple of cases that are dealing with some of the more serious challenges of working with that arise as people start trying to live on their own. But the number one thing that I've encountered is absolutely time management, and by splitting up deadlines and staggering rather than having one big deadline a week or one big deadline every week and a half, having 2 deadlines a week, it means that the feedback I've gotten is that students feel like the course is a lot more unrelenting. There's only like 2 times in the course after the 2 midterms where people can take a deep breath and be like, here are 2 days when I don't have to do homework for my course. But that means that they're not running into what they were doing before, which was, it's midnight, I've finished my programming assignment, and now I have to start the written assignment that's due in 8 hours. And then when I finish that at 4 a.m., I need to start working on my English paper. And so that's sort of, that's really been the biggest challenge. It's not that juniors magically know how to manage their time well. I'm 31 and I still don't know how to manage my time well, but I'm way better at it than I was as a freshman in college. And so, yeah.
All right, great, thank you. Steve, did you want to ask the question from Dutch?
Yeah, so Dutch would ask it himself, but his fan is broken down on his computer, so he's apparently touching it every once in a while to make sure it doesn't melt down. So Dutch wanted to know, in terms of setting learning objectives, how eager do you think we as educators should be to adapt what we teach to our students to trends in programming languages, in software engineering, in programming tools, in industry?
That is a question that very much, I think, matters where you are in the curriculum. I think that in terms of thinking about, and maybe even in terms of thinking about what courses to offer, we have a number of courses that are aimed at, we've got a web app development class, and I think that that's really cool. I think that's excellent, and I know that Kim Vol talked a little bit about this too, talking about, well, making sure that students have the ability to get started on their own projects. I guess her particular advice was, if you want to get into game design, like, be programming games. It doesn't matter if the university doesn't offer them. But in terms of, maybe the university should offer that, I think at the sophomore and the junior level, that's important. On the other hand, I think that in terms of the intro curriculum, we should be figuring out what people need in order to understand the foundations of computer science. And I don't think that there's just one foundations of computer science, but I mean, students are going to need to learn how to write imperative programs, and they're going to need to understand what it means to do a binary search tree, and they need to understand what it means to do a linked list. And I think that one of the aspects of that curriculum that I drew here on the screen a little while ago is that we have made in our curriculum a pretty conscious decision to make sure that people have a lot of fundamentals first. That we're not doing a lot of, we try to do interesting programming assignments that are fun and compelling on their own while people are working through this class. We teach arrays by doing image manipulation, and also we teach bit shifting by doing image manipulation. We do game search by doing or we do search problems by doing solving games. So we've got I've got above my head a lights out board. Woo! An old lights out board. We have them solve lights out. It's a simple computational game. And I've got some peg solitaire boards because we have them do peg solitaire. That's one of the assignments that we have them work on. So I think that, and the idea, the point of that curriculum, the point of getting a lot of fundamentals of data structures and functional programming and imperative programming is that once they've made it through that basic curriculum, once they've made it through that foundations, then there's a ton of places that you can go with that. Then there's a ton of directions that you can build off on that from. And many of the things that we should be doing are trying to explain and elaborate the connections between the fundamentals that they've then already learned and what's actually going on in the world and in the practice of computer science. But in terms of where I usually sit in the curriculum, in terms of the intro curriculum, I think that we should focus on making sure that they understand the foundational principles at work. And those are, at this point in time, we have a pretty clear sense, I think, overall of what those fundamentals are. They haven't changed. They haven't been. Linked lists aren't a fad, and so that's I think it's very worthwhile to make sure that that's a thing that is separate, that is its own thing. Now, again, you could disagree with the way that we choose to go about things and say, really, we should be working on more of these obvious connections to jargon going on in the real world than, and that should be first, and then we should use that to introduce some fundamentals. And I think that that's a possibly valid argument that I happen to disagree with, versus I think that there are some fundamentals, and that's kind of where I have the luxury of living in the curriculum, is this place where there are a lot of really core ideas.
Great. Will, can I jump in with one more question that I'm hoping to ask everybody before they escape us?
Oh, yeah.
All right. So, Rob, favorite teacher been, and can you tell us a little about them? Doesn't have to be computer science, doesn't have to be university level, just your favorite.
Say the beginning of the question again.
Who's your favorite teacher that you've had?
My high school physics teacher almost was the reason I went to school for engineering, and the reason that I thought I wanted to be an electrical engineer, because he was one of the first, I think, upper level. I took an AP course from him. He was effectively one of my first college level professors that taught with on a whiteboard. And so I'm more of a Blackboard person than a whiteboard person. But it was this idea of sort of explaining concepts live and in an improvisational fashion in front of students, where you have an idea of what you're teaching, but you're not actually, but you're working through that. And so that was, I thought that I wanted to be an electrical engineer because I knew I liked math, and I knew I liked computing, and I knew I liked physics. And I realized when I got to college that I really liked math and I really liked computing, and I'd really, really enjoyed taking Ken Gibson's physics class, and I don't think that's the fact that he didn't cause me to to fall in love with physics itself. I don't think, yeah, that wasn't going to be happening. That's not his fault. But I think I hadn't thought about the fact that he was also the first sort of college-level teacher that used live drawing. I distinctly remember that one of the things that I distinctly remember two things about that class. One of them was my friend who was an extraordinary math student and an extraordinary artist. Nalini lamented after Ken Gibson had drawn some demonstration of, you've got an elephant on a cliff and the elephant falls off a cliff and there's a trampoline and you've got the amount of like energy that's lost to the trampoline, and he drew this in like 4 lines, and it was very clearly an elephant falling off a cliff onto a trampoline. And Nalini was like, if I could draw an elephant like that man, I wouldn't be worried about getting into, you know, the conservatory that she was applying. He was incredible at communicating in this very, very minimal visual language. I mean, Picasso, right? And then the other thing was he had all of these, you know, demonstrations, and one of the things that he did was he had a DC generator that was just a pencil sharpener that generated, I guess it was AC current, and there was a little light bulb that you could screw in, and then there were 2 bare electrodes, and like, you know, he had us do the thing where you could screw in the light bulb and like you could put your hand on the. This was probably terrible, but he, you know, allowed us to experiment and play around and kind of maybe get a little bit hurt in a way that probably wasn't going to kill us, but you know, put a lot of trust in his students. So I haven't thought about high school physics in a long time. That's a really great question. Thank you for asking it.
You're very welcome. Will, do you have any more questions?
I guess sort of the very last question is always, you know, do you have any shout-outs or, you know, people you want to thank or anything you want to bring attention to or anything like that?
I am going going to blank at this point. I mean, I've mentioned I've had a lot of fantastic mentors in teaching at Carnegie Mellon, and in particular Frank Fenning and Tom Cortina. I could not have gotten to this place in one piece without both of them. So,
if we wanted to learn more about that class that you're involved in, is there a website that you'd point us to or materials online that we could find out more about?
Yeah, so basically the entire, all the course materials are available. They're linked from my website, which I think is linked from your website. And so we keep, you know, the course materials, and I think many of the programming assignments are just publicly available on the web. The compiler for the language that we use in the course, CNOT, is available from cnot.typesafety.net, and if you click on any of the instances of the course, then there's always a link to that website as well. So yeah, there's no textbook from the course. We're looking at consolidating our lecture notes into something that's a little bit more stable, not necessarily in a book form, but in a stable form. But for now and going forward, everything about the course is available on the web. So it's I'd definitely be happy to speak more specifically about that course with anyone that was interested.
Fantastic. Well, thank you very much. And you know, we had some really great questions from the audience today also. Thank you for all your questions. And I think we can go ahead and end the broadcast now, and if people want to hang around and talk for a few minutes afterwards, that'd be great. All right, well, thank you very much, Rob.
Thank you.
Thank you, Rob.
All right, signing off till the next time, where we have a guest that has not been announced yet, but we know who we have in mind, I think.
Summer vacation.
Summer vacation makes it harder. Okay. All right, thanks a lot, and see you all next time.